Hi, welcome to everybody to this webinar in measurement technology for hydrodynamics application. Please be aware that you are muted per purpose and that the webinar is recorded. My name is Pascal Erne and I'm business driver for test and measurement at Kistler. If you have any questions, please feel free to use the Q&A session on the right-hand side. We will answer your questions during the webinar, or if we can't answer them, so we will ask our specialist, Bill Zwolinski, at the end, or we are coming back to you via email. And now I'm proud to introduce you today's speaker, Bill Zwolinski. Bill holds a master's degree in electrical engineering, specializing in signal processing and controls. 20 years ago, before he joined Kistler, he was working in the field of underwater acoustics and was chief engineer for the Navy carrier landing system at Textron. Currently, Bill is working as a business development manager for test and measurement at Kistler and acts as an application engineer. And now I would like to hand over to our specialist, Bill Zwolinski. Bill, the stage is yours.
Thank you, Pascal. Appreciate that. Okay, so I'm going to take a few minutes here and go through some technology. And what I would like to do is also just brief you on the agenda. We'll talk a bit about piezoelectric principles of operation, some measuring chains, and we'll go into force, pressure, and acceleration measurement as well with some applications. And then we'll wrap it up in a summary with your questions and answers to follow. So, well, hydrodynamics in terms of physical measurements, there's quite a few opportunities to make physical measurements, certainly with test platforms of tow tanks, wave tanks, water tunnels, sloshing platforms, and so forth. There's a large interest in characterizing forces, moments, pressures, reaction of structures to waves, and just flow in general would be a very high interest. So there's quite a few opportunities to measure pressure, force, acceleration, and certainly the signal conditioning behind that is also of importance. Certainly, and I didn't mention here, but pressure distributions of wave impacts are also one of the areas that is of interest in this field research. And certainly I'll be talking a little bit about rise times and bandwidths and things to do with giving very good response time to events. Okay, so I think that could be a nice thing to keep in mind when you're deciding what instrumentation will fulfill your requirements. So in terms of piezoelectric, we're going to just touch upon with a force sensor. I mean, we're using basically quartz material, piezoelectric material. This material is integrated into a force sensor, and then we'll be talking quite a bit on what's called force dynamometers, which are platforms comprised of several of these three-component load cells. And basically, the way it works is there's a stress on the quartz, on the force sensor, and the output, charge is proportional to that force. Everything is calibrated, obviously, for that type of measurement in terms of picocoulombs per Newton, for example. And then with pressure, we have a couple different pressures. We have piezoelectric pressure, which is shown here, and operates in a similar manner where pressure equals force over acceleration. So you're stressing a piezoelectric material and you're getting a proportional output, which is calibrated for pressure. We're also going to touch upon a little later piezo-resistive technology, which is DC coupled versus a piezoelectric technology. Although it's quasi-static, it's also AC coupled as well. So we'll touch upon those concepts later on. And then lastly, acceleration. And this is illustrating here a accelerometer where you're basically using the concept of F equals ma to derive a proportional output from the accelerometer that's calibrated for vibration or acceleration. And there's obviously a piezoelectric sensor technology, a wide range, choices. And then there's also another one called MEMS capacitive technology, which we're going to touch upon, which gives the capability to measure DC response or very low frequency response with quite good accuracy. So we're going to touch upon a few different technologies anyway in this presentation. In terms of piezoelectric, the technology on the left here is basically piezoelectric is that there's no electronics inside the sensor. What that means is that there's an external amplifier, we call it a charge amplifier, which basically ranges the measuring chain. So you have near infinite rangeability for a piezoelectric measuring chain, and it's really based upon how capable the amplifier is. That's quite interesting to a lot of applications because there's often a wide range of forces and requirements that laboratories have to satisfy. So by having a flexible measuring chain that can be ranged externally, it often provides a platform that they can manage several different projects just with one set of equipment, which is pretty interesting to some. Obviously, with this type of measuring chain, the piezoelectric, it's also has a quasi-static capability, which I'll get into. So it can measure static events, over short periods of time, and you also have the ability to reset the amplifier and actually tear any, say, static mass or say a hydrostatic force, tear that off the sensor, and then you basically range the measuring chain for the dynamic range of the remaining portion. So you allocate the dynamic range of the measuring chain to the dynamic portion, which is sometimes of interest to some. Then the IEPE, we won't get into too deep in there, but it's basically a sensor with electronics. It's a fixed range, so you have no ability to range it externally. And it's basically only for dynamic measurements, so it doesn't have a quasi-static capability. What I want to say here with piezoelectrics is you're basically dealing with a lightly damped second-order system, and if you take a look at the curve here, it's just generally relatively flat in the passband, and it near the resonance, it definitely does gain in amplification or to the peak resonance. So there are some closed form expressions that I like to remind people of when they're using piezoelectric instruments. Now, these are rules of thumb, but the 5% frequency, natural frequency over 5, 10% is FN over 3, and the 3 dB is FN over 2. Now, why is that important? Is because in terms of measurements, oftentimes we're faced with satisfying certain frequency requirements. So what can be done is you can always work to design a platform that has, say, optimum frequency response for, say, a 5% frequency. But sometimes, that's not practical, or perhaps there's no budget to do that. And what you can do is you can broaden out the amplitude response range, say, take a 10% range, and accept the wider frequency. And this sort of is a compromise between, accuracy in terms of the 10% amplitude response versus 5, and usability, and obviously budgets are always something we have to keep in mind because that's the reality of our work. There's always a budget behind it. So it gives you a chance to adapt your measuring chain a bit. With piezoelectric sensors, you also have the low frequency response. I talked about it being AC coupled. So we term the low frequency response. You can look at this as a high pass characteristic, okay? And basically, it's a single pole high pass characteristic, which I show here in the left hand side. And basically, that's given by a simple transfer function in the Laplace domain. And you can then derive, the 5, 10, and 3 dB points on the low end. And what happens is you can then determine, by knowing what the time constant is of your system, you can simply compute what the low frequency response is. So in this case here, if I just take these are the parameters of time constants, I can then compute the short, medium, and long time constant, and you can see that in some cases I could have a 15 hertz low end, or a 1 hertz low end, or even be pretty much quasi-static right near 0 hertz. Obviously, with quasi-static and piezoelectric, the amplifier does have a small drift component, which is an attribute of a piezoelectric system optimized or in long time constant, which is optimizing for 0 hertz. So we'll get into that a bit as well. So the quasi-static and dynamic measurement, pretty straightforward. With the dynamic amp, you're measuring pulsations, you're measuring continuous waveforms. Obviously, anything, say, purely static is not going to be possible with a dynamic amplifier, but a quasi-static amp for sure can do all of these, and certainly with a long time constant, this static event, can be measured. And again, drift might become visible after a long time, depending on the forces being measured, the magnitude of the forces being measured. And this is just another illustration of quasi-static measurement. It's a busy chart, but basically what we're trying to convey here is that the time constant is a important parameter to your decision on measurement. What I show here, and if you just see the illustration here on the below, if the input force is constant, if you have too short of a time constant, you'll get an exponential decay. Okay, but if you have a long time constant, you get a static signal out. And that's really the concept behind time constant, is that when you have a short time constant, you basically cannot do any quasi-static measurement. But in amplifiers, in charge amplifiers, what you'll find is that there is a small drift component, and it's given by a parameter called 0.03 picocoulomb per second. Picocoulomb is a measure of charge. So this is basically the amount of drift per second, okay? So if you just take an example of a typical sensitivity, you can see that you might get upwards of a half a newton a minute in Z, or perhaps a quarter newton per minute in X and Y in the shear. Just as an example to give you a flavor. Now this is typically the maximum to expect, and quite often it's much lower, but it's anyway spec'd out. And anyway, when you have large forces or large events or large magnitude events, I mean, these types of figures over a couple minutes are not substantial, and in some cases you can use a drift compensation algorithm to remove them, and that's certainly something that's done also in the industry to remove the amplifier drift, as it is a linear parameter and can be compensated for. In terms of the rangeability of a piezoelectric measuring chain, I'd like to illustrate this a bit. Say you only have one sensor, okay, and that sensor is perhaps rated up to 10,000 newtons, all right, and the sensitivity is 4 picocoulomb per newton. With an amplifier, with a charge amplifier, you can range this measuring chain for 1 newton full scale, 25 newtons, or up to 10,000 newtons full scale. Full scale means 10 volts, plus or minus 10 volts, right? So what happens is that you get the rangeability, but you also get the benefit of noise reduction. If you had this 10,000 newton sensor, and this is all you had at 0.6 of a newton RMS broadband noise, you might be limited on the low end in terms of resolution. However, if you just range it for a lower value, you see that the resolution becomes much better. And that's really a powerful tool that people use with piezoelectric instruments. And again, like I said, if you have a static force acting upon a sensor, say it's a weight or the weight of a test article, you can basically null that out in the measuring chain and optimize on the forces that are being subjected to the test article. So it gives you the ability to really optimize your dynamic range. This is basically what I say here, is that any static mass can be teared out, and this gives you the ability to optimize your dynamic range of the measurement. Well, so now we've gone through a little bit on sensors, on piezoelectric technology. Now what? Well, you have to be able to, obviously, have an amplifier and then, acquire the data. So quite a few options in the field of data acquisition nowadays. What I show here is really a platform we call LabAmp, and it's quite unique actually, because it's a very high fidelity charge amplifier, but it also has integrated data acquisition of 24 bits and very workable sampling rates of 100 kilosamples per second, or even up to 200 kilosamples per second, depending on the amplifier. So what's going on anyway is, as this integration of digital signal processing and classical charge amps is really on the forefront of the technology people are using nowadays in terms of doing this. Obviously, these amplifiers can also output analog signals. So if there's existing data acquisition systems, it's simple enough to take the analog outputs and route them right to the data acquisition system on site. Lastly, with any digital data and any multiple devices collecting or digitizing data, there's also the interest to keep data synchronized. So nowadays, there's a standard called IEEE 1588, and this is a PTP, or Precision Time Protocol Synchronization. Certainly with these amplifiers are software tools that actually are very transparent. So what happens if you have multiple devices, sampling, multiple channels, this data is time synchronized to better than 1 microsecond by the software using this PTP synchronization feature. So it's quite a bit of detail behind this, but very usable, and it's very transparent to the user. You hardly know it's going on, because the software basically takes care of the alignment and gives you a common time base in the data file. Obviously, a lot of software options nowadays, and depending on the requirements of the test, that dictates what software. And what I wanted to do, that platform is primarily for piezoelectric, but there's obviously other platforms out there that are of interest. And certainly when you're doing hydrodynamics testing, you not only, you might be using piezoelectric sensors, you might be using strain gauge, you might be using pressure sensors of various technologies, and temperature sensors and so forth. So having a platform that can adapt to whatever measuring you might have is somewhat powerful, okay, in the laboratory environment. And certainly this KeyDAC platform is basically certainly capable of doing that. It's can interface with a multitude of sensors, not only say Kistler sensors, but sensors you might have in your lab already. It interfaces to various equipment on the Ethernet interface. And it also has a software component too called Key Studio Lab, which allows you to coordinate the data acquisition projects and data acquisition approach to your measurement. But nowadays, these types of say multi-purpose systems are quite common in laboratories, where you have perhaps the ability to measure up to 20 or more measurands. In this case, I show you some examples, and certainly some of these signal formats and sensors are very common to the hydrodynamics environment. But certainly having the ability to build up a scalable and modular data acquisition platform is often quite flexible to the laboratory, and in that a lot of times they don't know what might be coming a month from now, or 2 months from now, or a year from now, and having a platform that can adapt is helpful to be able to satisfy the requirements of a given test. Obviously, with software, I talked about that earlier. There's this Key Studio Lab, and that basically allows you to coordinate the various data acquisition and projects to do with your test and measurement application, hydrodynamics. JBeam is a visualization, analysis and visualization program that basically has a very powerful reporting feature that, as you say, graphically develop your analysis and solutions, you can generate reports quite readily and quite easily. So it's quite a interesting package for some, and it gives quite a bit of capability to document and to analyze. Obviously, with these types of modular platforms, there's a lot of different features and benefits, and certainly, having external triggers is one. Live graphs, FFTs are quite the basis for a lot of our analysis nowadays. Certainly, J-beam analysis provides the ability to do more elaborate FFTs, graphical displays, 2 and 3D axis charts, and so forth. So when looking at software and analysis, as well as the modularity of platforms, it's often good to get an overview like this to see that in a hydrodynamic solution, there's usually a multitude of signals that need to be acquired, and they need to be acquired in a time synchronous manner. So the platform, anyway, the signal, the sensors, signal conditioning, and platform really complement a hydrodynamic solution in many ways. So what I'd like to do now is just segue to the force and moment topic, and we talk a little about force dynamometers. And what I mentioned earlier was a force dynamometer, and I'm sort of blocking the picture here. A force dynamometer is comprised of several three-component force sensors. And what you see here is usually comprised of a top and bottom plate with force sensors in between, and you're using this plate primarily to distribute loads over a large area. Force sensors, single force sensors like this, operate very well when you have axial forces. But in a lot of hydrodynamics applications, you might be testing a model or doing some large structure, a coastal structure, and you're trying to understand the dynamics behind it with regard to certain inputs due to flow. So what happens is that is not an axial input. So you need to, using a dynamometer, a force dynamometer allows you to distribute those loads amongst the sensors and then be able to geometrically calculate 6 components, which I'll get into shortly. Obviously, with any measurement like this, there's analog bandwidth considerations, and this is something that always of interest is the charge amp is always going to give you a wide bandwidth, but the test articles are going to require a certain amount of bandwidth as well, what your frequencies of interest are, and lastly, when you put the force sensors together to measure it, do they actually fulfill those requirements? So it's a bit of a step-by-step process to develop the right platform, but a lot of times these platforms are also modular and can be reconfigured or perhaps even rearranged, like I said before, to accommodate a wide range of test articles. I'm probably not going to go into each one of these right now, but there's a lot of considerations when you get into force and moment measurements. I am going to touch upon a few shortly. But these are design considerations from installation and mounting to sensor selection, mass loading, frequency response, and so forth are all critical things to keep in mind. So we're going to get into that shortly. What I wanted to do was just touch upon a little bit on three-component force sensors. Usually what people will have is they'll have choices in sensors themselves or what we call force links. Force links are preloaded force sensors at the factory, which come with a calibration circuit, basically pre-calibrated based upon this top and bottom flange and preload bolt. So they're very useful modular tools that out of the box have a calibration certificate, and they're modular building blocks, if you will, for various dynamometer solutions. What I show here is some typical terminology, sensitivities. And a lot of times with quartz products, you see common sensitivities, and you do for the middle range products. This product here is not quartz; it's piezostar. With the higher sensitivity, it's giving better resolution and lower drift in applications, and it's often used, in applications we have with hydrodynamics facilities. It's where forces aren't extremely high. As you can see, the maximum Z range is 3 kilonewtons, and X and Y is 1.5. So, they do offer a good capability, but what's really powerful is the higher sensitivity. And that's quite interesting. Obviously, what we like to do is characterize the stiffnesses of all because when you're doing your FEA models, you're trying to figure out, hey, will this work for my application? We need to characterize CAD models and provide all the relevant stiffnesses so it can be done in a proper manner. And obviously, one of the nice things with piezoelectrics is they're inherently low in crosstalk. As you see here, I mean, having 1%, 2% figures, and these figures are really the upper bound, and in general they're quite a bit less, and I'll show an example of that. But when you're actually putting together such a dynamometer, there's no compensation matrices that need to be used like in a strain gauge based multi-component platform. These are inherently, well, they're rigid and they're inherently low in crosstalk. So it does, from a bookkeeping and from a managing standpoint, provide a little bit less work in the end in that regard. So what this looks like is basically this three-component load cells. And what we have is we do some pre-summing in the middle. So we should have 12 signals, 4 sensors, 3 outputs per sensor. And we do some pre-summing, and we're ending up with 8 signals on the output of the dynamometer. What's interesting about this geometry, you see the A, which is the vertical separation of the center of the force sensor to the middle of the dynamometer, and you see B, which is the horizontal separation from the center to the force sensor. By knowing the geometry, you can calculate forces and moments in 6 components using this closed form set of expressions, which is pretty common. Some amplifiers like this will have an integral summing calculator that actually outputs 6 analog signals using this methodology. I'm just going to touch upon a little bit on if you had to build your own dynamometer, what are those considerations? And obviously, I talk about load-bearing surfaces, and we have requirements on flatness and parallelism. Certainly, strength of materials and stiffnesses are all factoring in to the ability to measure at the required frequencies, for example. Preloading is always important with a piezoelectric sensor. With 3 component sensors, preloading gives you the ability to have linearity, gives you the ability to have compressive and tensile force handling, and also shear force transmission. The shear force transmission in a 3-component load cell is basically given by the amount of preload force times the frictional coefficient of the load cell. And what we do anyway is we provide a ceramic top and bottom coating on the load cell, which gives a frictional coefficient of 0.2, and so you get about a 20% transmission of shear forces compared to the preload of the sensor, and that's pretty powerful as well. Certainly with linearity, this is one of your largest error sources in measurement because it relates the input versus output, and that in itself will dictate the accuracy. So having very tight linearity is often a goal. Certainly with linearity with force sensors and in fact pressure sensors as well, you can do partial range calibrations. And if you see here, we calibrated this at 450 kilonewtons, very large range. But if it's at 0.5% FSO, but if you calibrate just on a 45 kilonewton range, you're at a linearity of about 0.13. So by being smart on how you calibrate, and you can have basically a lookup table depending on what tests you're measuring, and dial in the right sensitivities to get the optimum accuracy for that measurement. Pretty interesting. Certainly with preload shunt force calibration, I mean, these are forces that basically the calibration of a preloaded force sensor is about 6 to 9% lower because the preload bolt is mechanically in parallel with the sensor, so there's a shunt effect there. It's calibratable and it's constant, so it's pretty much well understood in the piezoelectric instrumentation arena. Certainly with tensile and compressive forces, by preloading to a high level, say 2/3 of the full-scale measuring range, you're left with plus or minus 1/3 of the usability for compressive and tensile forces, and that's pretty powerful as well. Alignment of force sensors, very important. It reduces crosstalk. So having the ability to align sensors And you'll see force sensors are actually, they appear to be round, but they actually have flats on either side. And these flats allow you to align the sensor to a straight edge, to a straight, and which is important to alignment. And then lastly, crosstalk. The rated crosstalk on the data sheet is quite large compared to what the actual results show on the calibration cert. As you can see here, we're upwards of say 3% between X and Y and Z, and you can see here we're quite a bit lower than that. So a lot of times manufacturers will put in a top level spec in the data sheet, but oftentimes, at least with Kistler, we're quite conservative in how we spec, and you're achieving much better crosstalk than on the data sheet, which the data sheet is even quite good crosstalk, but you're even getting better in the real sense. So an application of a tow tank or a wave tank, and here you are, you have a carriage, and you've got a ship model, and you're actually going to build a dynamometer, in this case full of force links, okay, 4 force links. And in this case, the user didn't decide to do some pre-summing. They wanted to take those 12 signals and put them into an amplifier, and then go to a computer and resolve the forces and moments from there. Pretty standard application. And because you're using force links, this is quite a modular approach. You can make bigger or smaller dynamometers very easily. Also, because of the rangeability of the amplifiers, you can easily stay with one size dynamometer and just range it for various applications. And this is just a slide talking about the products which I've already done. And this is just an example over at the University of Michigan Hydrodynamics lab. You can see they used a 3-component, this 9317 3-component load cell. This is the piezo star version. They built a top and bottom plate, sandwiched these 4 units in between the plates, and you can see here where they screwed in from the top and the bottom, and then they put a holding mechanism at the top. And obviously this is a picture of their tow tank. This is just showing how the engineers were actually outfitting the boat model with the dynamometer. And you can see here that the dynamometer is now resident in the boat, and there's a pole that's coming up to the holding mechanism on the carriage. This is actually the carriage that rides up and down the tow tank, and this boat is actually in a reservoir on either side of this carriage. You can see the water right beneath it. So it's quite a large scale model anyway, but they have a very good workspace here above on the carriage to collect data and to configure models and such. So how does this all work? Obviously, we've got instrumentation, which has IP68 rating. Okay, and there's many ways to look at this. In this case here, you've got instrumentation, force sensors, and you've got cables. And these are detachable cables that are rated at IP68 for, say, a 13-bar operation. Okay, so tow tanks are nowhere near that deep, but certainly other applications might require that kind of resistance to pressure. You also see individual force sensors. You see on the bottom here dynamometers. There could be an off-the-shelf dynamometer, and there could be actually a dynamometer that's made by the user using these force sensors, where these cables basically come up to signal conditioning outside the water. So you see here the water level. We show the signal conditioning is outside of that. Okay, so these are basically charge signals going up to the surface, and this could be a carriage of a tow tank, and you've got these amplifiers up there, and everything's watertight and sealed. Now we know there's also applications, and we work with several companies that are doing more elaborate testing where the actual model is self-contained and has a watertight compartment, and that way there's no cables coming up to the surface. They want everything integrated within the model, and these often require voltage output sensors, which I'm going to talk about shortly, where there's no charge amp required. It's all integrated, and you just got to go right to your data acquisition system, which is in this watertight compartment. So we talk about immersion in water. Well, that can be certainly a depth related, or in some applications where you have water tunnels, it could be related to also just the pressure in that vessel. And these are just the cables that we refer to, the 1698 AI and the AB. One's an armored cable, one's a more flexible cable, both qualified to 13 bar, 189 PSI. And there's also a breakout cable that goes to 3 B and C's, X, Y, and Z, and that goes right to your signal conditioning. This is another example of a wave pool, but it gives you an example of a voltage output sensor. And there's been a very long historic product at Kistler anyway. It's a 3-component sensor that's got integrated electronics that gives a voltage output. What's really cool about this sensor is that it's long time constant, so it's basically a DC coupled sensor. So if you've got tests where you're actually doing, say, low frequency or hydrostatic loads on structures, you can measure this with these types of systems. And because it's a voltage output, it can be integrated directly into the model. And through this watertight compartment, the data acquisition just takes care of it right from there. So there's no charge signals going up to an amplifier outside the water. It's all self-contained in IP68. Now, this is probably going to be phased out very soon, and we are also looking at other solutions. Certainly, a custom submersible solution where you have an inline amplifier, three axis amplifier, and this can convert any force sensor in the portfolio to a voltage output. So this is also being used nowadays to interface to these watertight compartments in models and so forth. And certainly it's a voltage output sensor, 2 ranges, and time constant selections. Lastly, there's also custom dynamometers, which basically can do prop shaft studies where you've got external slip rings in the vehicle to get the signals to a data acquisition system. So, and there's many ways to do it, but fundamentally, charge mode sensors going up to the surface through charge amps, or we can have integrated voltage sensors that are going to give you voltage out, which can go through slip rings, go right to data acquisition systems straight away. And then another one I want to point out is there's a direct measurement with a 6-component force. This is being used, with those cables I just referred to. And it's small. It's only maybe 90 millimeters high by maybe 60 millimeters OD. And these can be located behind geometric structures in flow to measure 6 components directly with no calculation. And obviously it would be rated to 13 bar as well. Also, a kit that you can consider for making your own dyno is a 9366cc kit. And there are certain guidelines. Obviously, steel plates, aluminum plates could be an option. Certainly, the Young's modulus of steel is certainly it's 3 times stiffer than aluminum, but aluminum's much lighter, so you get less mass on sensors, higher frequency response. And we just show an illustration here. But we were faced with a question from one user that said, "Hey, I've got a large structure up to say over 1,000 kilograms, okay, and we want to be able to measure forces and moments of this, but my forces are up to 20 kilonewtons vertically and horizontally, and up to 15,000 newton meters, okay." Well, using this kit, you can achieve this type of performance. It's a 2-meter deep basin, water flowing. Make your own dynamometer. Obviously, a custom one would be the best performance, but like I said before, budgets are always tight, so you're always trying to find a way to make it work and make a good measurement with a limited budget. So there are options in that regard, and I just highlight this as some of the flexibility that piezoelectric instrumentation brings. Just a quick one here, just touching base on the dynamometer as a spring mass system. So you add mass, you're going to decrease frequency response. It's pretty straightforward. So there's always a trade-off between size of dynamometer, mass that you're testing, and frequency response. And certainly your local application engineer can handle a lot of these questions if you have them. But certainly direct some to us if you want to know more. And obviously mounting is also important. There's a lot of different dynamometers off the shelf, but mounting dynamometers also is very important to achieving the best frequency response. Just like if you're trying to mount a sensor, you want to get the best out of a sensor, mount it properly. Whatever the manufacturer says, if you follow those rules, you'll get the best. So this is not a surprise that mounting is an important parameter to getting the best frequency response out of a force sensor. And then lastly, calibration. There are ways to do in situ calibration, certainly at your facility, but certainly at the factory. You can do this electric actuator press with calibration. Force sensors, reference sensors can really be used to characterize multi-component force platforms. And oftentimes, they're used in that regard. And, the calibrations are quite detailed with crosstalks, linearities, and they could even do partial range calibrations as well. And I just want to mention bonded foil strain gauge. I mean, like I talked about piezoelectric, I mean, you've got a very rigid structure where you're basically stressing a crystal and you're getting a proportional output. With strain gauge, you've basically got a flexible structure, and you've basically got a Wheatstone bridge circuit behind it that's basically deforming and changing resistance, which is then proportional to force. So totally different concept to piezoelectric. It's based upon flexibility, and piezoelectric is based upon rigidity. With that said, there's always a comparison. People always ask me, well, make a comparison. It's extremely difficult to make comparisons on technology because it's so depending on applications. But, what you see here really is no surprise. Strain gauge is actually absolutely the best if you're doing static long-term measurements. It's very good with temperature compensation, very proven technology, good range and temperatures, good accuracies, and so forth. So, I mean, where sort of the weaknesses of strain gauge are really the strengths of also piezoelectric, and you can see sort of by the picture I show there is that, the quasi-static capability of piezoelectric, a lot of times can satisfy the application. Sometimes the strain gauge is going to be needed. Okay, but it's application dependent if a piezoelectric is suitable. Obviously, there's rangeability we talked about, flexibility, modularity, low crosstalk, all those things that made it, I think, an option anyway for many of the hydrodynamic labs we work with. And then obviously I talk to a lot of hydrodynamic labs. What they tell me is, hey, piezoelectrics with natural frequency response time is very important sometimes, but certainly natural frequency is even more important when you have, large masses and you're doing large structural testing. You want to be sure that you've got the frequency response. I'd say the predominant thing I hear is test stand adaptability. Where you can range it and it's modular. You can easily put together different systems quickly and calibrate them in situ. And I'm being told many times, Bill, this is really saving budget to have something like this because now I have everything I need and I just have to adapt it to my application. And obviously quasi-static is also a parameter, and that has to be looked at for your range of applications if the quasi-static capability satisfies or not. So your application engineers can help you on that. Checklist, I went through a lot of this, and I won't go through it again, but there's a checklist of things to consider when doing force platforms. Then we segue to pressure, and with pressure, with piezoelectric, it's very complementary to having very small OD pressure sensors. And the same rules apply. Quasi-static capabilities with piezoelectric, dynamic capabilities with IEPE. You have the measuring chain flexibility, as I talked to with piezoelectric, rangeability, time constant variation, doing quasi-static or dynamic. You have quite a few advantages on the piezoelectric side versus an IEPE side. But again, there's always a decision with technology, and it relates to the application. So we have to look at the application a lot of times to determine the best fit technology. Obviously, with technology, we also have piezo-resistive pressure sensors, and certainly they operate on the same concept I talked about earlier. You have a piezo-resistive bridge, and a deformation of the diaphragm changes the resistance. That resistance is then proportional to pressure, and obviously the whole thing is calibrated as a pressure instrument. Many different technologies with piezoresistive. The one we use is a cavity etch micro machine silicon sensing element. And on this technology, you basically get some real benefits with the silicon-based technology. You get a high gauge factor, which is extremely important to getting better sensitivity out of your sensors, and certainly high overload capability. So now you have more forgiveness in your sensor, in that if you have a bad day of testing, you didn't have to buy a whole range of new sensors, for example, by having a higher overload capability. Certainly, frequency response, yeah, these are optimized for DC, but they do have a bandwidth of 2 kilohertz, and certainly that would give you a couple tenths of a millisecond type rise times, which is quite useful in dynamic measurement as well. In terms of various pressure measurements, I mean, piezoelectric optimized for dynamic and pressure pulsations, and the quasi-static, like I said, is the area where you do see some drift over time. A lot of times that's quite usable for the application range of hydrodynamics. And with piezoresistive, you're talking low bandwidth events, pulsations, or low bandwidth pulses. And certainly static pressure is really the strength of the technology, and long-term static pressure measurement is absolutely the one area that piezoresistive does well. And certainly there's a checklist of parameters and in terms of measuring range, frequency response, and so forth. And these are some of the things that your application engineer would talk to you about, and making sure that the right fit is within your application. But in that regard, just want to touch upon a couple things with piezoelectric sensors. You can see here in this case here, you have a quasi-static type event, long time constant. You get this ripple on the event. Well, what you can do is you can actually, if you go to a short time constant, you get rid of this offset, this static offset, and you just optimize on the dynamic portion. So this small ripple now is extreme high fidelity, because now you've optimized that with a short time constant. In some applications, it might be meaningful to have the granularity for that. And certainly you can look at this time constant feature to help in that regard. And certainly with quasi-static events, we often guide people to choose the right time constant. We want to make sure that the time constant is at least 100 times the event duration if you have, say, a transient event, to get the best performance. So yeah, there is some detail behind a time constant, but it's very usable for hydrodynamic applications, and certainly something to consider. I mentioned natural frequencies. I mean, natural frequency and rise times are all complementary, okay? See, the natural frequency is inversely proportional to rise time, and rise time is inversely proportional to natural frequency. So if you need fast response, you want a wider bandwidth, wider natural frequency, and that gives you faster rise time, faster response time. So in some applications, it might be rather critical. Piezoelectrics can offer, microsecond level, response times, which is probably far beyond what most hydrodynamic applications require. What we show here is a really interesting example where you have maybe an 80 microsecond pulse, and you look at different bandwidths. And what you see here is that if the pressure sensor is 100 kilohertz in natural frequency, you can easily resolve this type of sharp event. But if you go with a 10 kilohertz or even a 1 kilohertz sensor, you can see that in the 10 kilohertz, you've basically got a damp sinusoid, and you've excited the resonance, and it's really not too useful. And in the 1 kilohertz side, you've got basically a highly low pass filtered event, so you can't measure this sharp event. Again, technology is the determining factor. Which technology is the best? Well, what events do you have? What is the best fit? Rise time is a parameter that's often important to our scientists that we deal with and researchers. And yeah, it's related to bandwidth, and yeah, bandwidth's related to technology. Is it a strain gauge based? Is it a piezoelectric based? And finding the right balance there is really achievable in a lot of cases. We now have submersible PE and IEPE pressure sensors, and this is using a welded cable to it's a Viton cable to a very piezoelectric pressure sensor. As you can see here, that's a very much a sealed and well behaving type interface of a welded cable to the sensor itself. And these are the sensors that typically people will consider. Okay, you have a very small diaphragm of about 5 millimeters. Okay, and that's huge benefit for when you need very good spatial resolution in your water impacts. You also get this rise time also benefit because of the wide bandwidth. In this case, you have a 215 hertz or kilohertz natural frequency. You're at a 1.4 microsecond rise time. So a lot of times that kind of speed is not required, but it's certainly very fast and very able to give you high fidelity measurements. The other thing is with this sensor anyway, it has a low thermal shock sensitivity. And a lot of times when you get with impact measurements, you wouldn't think the air pressure or air temperature and water temperature would be that much different. But a lot of times you're not measuring high pressures, okay, with impact. So those difference of temperatures of water and air can be problematic in terms of a measurement. And having a diaphragm that's specially designed for thermal shock is really cool in terms of mitigating any thermal transient errors in the measurement. So certainly the 601C provides those features all in one and very small sensor. And then there's a 603 for higher pressures on up to say 1,000 bar. And it's say a workhorse sensor for many applications in terms of measurements, but it also has small dimensions, fast rise time, wide temperature range, and so forth. Just a little bit of an example of a wave impact. What you see here is these sensors tightly spaced, and what's nice about these sensors here, they got such a small diaphragm of 5 millimeters. You can tightly pack those, and then you can flush mount them. They absolutely love to be flush mounted for this type of application. They work very well. But you see here that it's very important to have a stiff structure. You want a structure that's not plexiglass preferred, because plexiglass bends. It's got a very low Young's modulus compared to steel and aluminum, and the bending could actually couple in and make errors in your measurement. You want them flush mounted. You can see here these sensors are some are sticking out, some are recessed, so it wasn't a high precision mount. But anyway, it's a mount anyway, and you want flush mount because it gives you the best characterization of the water impact. And obviously, direct mount of a sensor is often required to get the tightest spacing of the sensors. But also, we also encourage people to use adapters, like in this case, where the adapter actually accepts the pressure sensor. Then you have a much bigger thread to just screw into the to the frame, to this plate, and it's a little bit easier overall to manage the large number of sensors. So again, it's really application dependent, tight spacing, direct mounting. If the spacing isn't as tight, you can maybe use an adapter. And certainly this would be an example of what a typical wave impact would be. And there's also cavitation water tunnel testing using pressure sensors. In this case here, you have a pressurized closed vessel. You've got maybe a test article where it's a propeller, and you have pressure sensors that are, say, mounted above that. And these pressure sensors are monitoring cavitation, for example. Okay, where you see some examples here with and without cavitation, and you can see the profile of the pressure pulsations. Obviously, cavitation tunnels are not only used for cavitation; they're used for noise and vibration measurements. They're used for forces and moments. We work with companies doing dynamometers within these structures, and certainly accelerometers are often used. And certainly there's a classical dynamometer in back that does the torque and thrust measurement of the test article as well. Then you see applications to do with sloshing. Sloshing is often considered when you're doing LNG tanker studies, where you're looking at obviously ship stability as LNG is sloshing around in high sea states, and just with travel on the ocean. So there's a scientific approach behind that, where you use a hexapod and a tank, And on the tank, you will mount sensors of high spatial density, very tightly packed, as you can see here. In this case, this is actually a metal plate, like I had recommended before. So it mitigates any bending of that structure. So although you have a plexiglass tank, you have a metal insert that basically fits onto the tank and allows you to measure with high density these water impacts, which are at very low level. And if you're using the right sensor, like we said, the 601C has that very well-respected thermal transient response. You get basically out-of-the-box measurement of high spatial resolution as well as low thermal errors, and basically all in one. Pretty interesting, and certainly with the high bandwidth, you get the fast rise times as well. Acceleration and shock, I got a few minutes left here. Basically, yeah, acceleration, vibration, shock, those terminologies are often thrown around, but they're different, okay? So acceleration could be both static and dynamic events. If you've ever ridden on a racetrack, I mean, you see there's periods of static acceleration or constant acceleration and dynamic. Certainly, if you got a gear train, that's a constant, that's a continuous vibration, and that's what we call vibration. And certainly shock is a short duration transient event, okay? So all of these can be measured with accelerometers, okay? And they're just different terminology. Certainly I give you a table here just showing certain, G ranges for certain events that happen in our life. Certainly auto braking is less than 1 G. We often do that driving to work. We don't drive fuel dragsters, but they're up around 3 G. And so forth. And certainly explosions are upwards of 60 to 100,000 G. So yeah, same basic rules, PE and IEPE accelerometers. Piezoelectric has the ability to have a charge amplifier external, so you get the rangeability. You get, basically with acceleration, you generally don't do quasi-static acceleration, but it could be done. A lot of times there's other technologies that are used in that regard. And then with IEPE, it's probably the more predominant approach because vibration is dynamic. There's no quasi-static component to it, as I showed earlier. So piezoelectric or IEPE, integrated electronics piezoelectric, ideal fit for vibration. And I talked about MEMS capacitive accelerometers. MEMS means micro electromechanical system. It's basically, for lack of a better term, a spring mass system suspended on a cantilever beam, if you will, within these two electrodes. And as this spring mass moves up and down by virtue of the acceleration, there's a change of capacitance between the spring mass and the top and bottom electrodes. That change of capacitance is then directly proportional to acceleration. The accelerometer is calibrated for that, and you now have the ability to measure both dynamic and static acceleration all in one. So a lot of times you can measure tilt with these sensors too, because you have a local gravity capability. Tilt measurements are basically easily computed using a MEMS accelerometer. So if tilt is an issue, you can use this for vibration as well as inclination measurement. The frequency response, as I said, variable capacitance sensors are flat at DC. They're DC coupled, or piezoelectric or AC coupled, and you have this peak resonance. Whereas capacitance sensors are MEMS capacitive tend to be critically damped or damping around 0.7, and a very graceful behavior. Comparisons, yeah, I'd say the main comparison is measuring range and frequency response. We're using one technology over the other. Obviously, with wave type of studies, MEMS capacitive are pretty cool because they give you 0 hertz. So you can have, see states that, fairly low with low frequency type motion, and you can actually measure that with a capacitive accelerometer perfectly because it has true DC response. And then obviously with all these types of signal formats, we have integral cable solutions that are IP68 rated, and this is a triaxial version. The triax is about 10 millimeters, 11 millimeters cube, okay? Whereas, and it has a wide range from 50 G on up to 2000 G. Wide frequency response, usually satisfying easily, up to 5 kilohertz and even higher, up to 10 kilohertz, 5%. There's also single axis versions, again, with integral cables, IP68 at 10 bar, 145 psi. And these are often used in hydrodynamic studies as well. And certainly the same type of G range selections are available. And then triaxial MEMS capacitive accelerometers provide you integral cable, IP68, 10 bar operation, again, fully submersible and usable in a hydrodynamics setting. So anything to do with structural vibrations, how flow affects structures and vibrates, how impacts affect structures and so forth, all can be measured with these accelerometers. And then certainly there's a checklist with all these accelerometers too. I touched upon several of them already, and certainly your local application engineer could help you make the best choice. But certainly a wide range of IP68 and accelerometers to make a variety of different measurements. And lastly, I just wanted to mention we do test all our integral cable sensors in a pressurized vessel, and they have a certificate, as you can see here. So these aren't just put together and hoping that they work. They're actually been engineered and certified for underwater testing. And then lastly, just an overview on all the different applications we touched upon. Obviously, tow tanks and the variety of measurements there. Wave basins and slamming, we talked about rise time, and pressure sensors, for example, sloshing, we talked more about pressure sensors. Propulsion system, pressure sensors, but there's also other components, whether it be force and vibration. Flow-induced vibration, structural vibration in shipping, and also structural dynamics, modal testing, all can be accomplished with these types of sensor technologies. We covered a lot of ground today, and I'm just at the limit of my time, so I'd be happy to answer any questions. I know there was a lot to digest in this session, but we are very excited to answer any of your questions. If we can't handle them or can't get to them in this time frame, we'll certainly respond to you offline. So at that point, Pascal, would you like to jump in and let me know if there are any questions?
Yes, please. Thanks a lot for this very nice presentation, full of information. Yes, there was one question about the limitation of the cable length for piezoelectric sensors. Do you have some information on that?
Yeah, typically I recommend on the 20-meter side, but we've gone even longer with piezoelectric. So it's really a function of what signal levels. I'd like to know what signal levels you're trying to measure, but I'd say just rough figures 20 meters. But I'd say let us know on your application engineer what type of signal levels you're looking at, what type of distances, and we can make a calculation to see if longer lengths are possible. Now, with IEPE formats, you can go kilometers, okay? There's no limitation really, or there's very light limitation, but with piezoelectric, you do have some shorter lengths, but in a ballistics environment, for example, we might go 60 to 80 meters because the signal strength is quite high. So give us an idea of what your signal levels are and what your application is, and we can maybe guide you a little bit better. But the general rule is 20 meters.
Great, thanks a lot. Then there was another question about force sensors. So there is a nice application of a force sensor in the water, as on the water, and there is an electrical generator next to the sensor. So I think the 2-bar issue already explains our sensors are well prepared to be used on the water for 2 bars, but what about the strong magnetic field close to the sensor?
Yes, strong magnetic fields are always a concern. Okay, and what you like to do is certainly it's sometimes sensors can be actually tested for, say, a magnetic field strength or sensitivity with magnetic fields. But the actual strength of the magnetic field is important. But also, I often look at, is there ground isolation? Is there cable routing? The cable, in my experience, is often one of the biggest weak points of electromagnetic susceptibility. And, so we want to route cables in a smart manner. So the short answer is yes, every sensor is going to be sensitive to electromagnetic fields, but it really depends on the field strength, the closeness of the sensor, and certainly, the way the cable is routed. Is it ground isolated? These are the factors that sometimes can play a role. Sometimes, again, depending on the sensor, there might be recommendations we can make to make it more usable. But in my experience, it's one of these things where you want to do a test. And oftentimes we have demos that can be used to make a test in your environment. It's empirical, but it actually gives you a quick result and to see what the effect is. But yeah, there are ways to mitigate, using, shielding, extra conduit on the cable or other techniques. And there's, it's really application dependent, and we're happy to help and guide in that manner. But I often like to do a test to see the magnitude of the issue, facing us with these types of applications.
Yes, great. Thanks a lot. So once again, this webinar was recorded. So if you missed any information, you can rewatch the webinar. So the link will be shared with you within the next few days. And if you have any other questions, so just feel free to contact your sales, Bill or me directly. So we'll be happy to answer your question. So thanks a lot for listening, and speak to you soon.
Very good. Thank you. Thank you all.